Hi there, my name is Bruce, and this video is about a radius tool that I built. I have a need for a project to make radii, machine radii, both internal and external radii, offset from the center line of the lathe. So there's a lot of designs to make balls, ball turning tools and so forth, but you've got to, it's more difficult when you have to get off the center line, so, and by a precise amount. So this is what I built, and I'm just going to show you what is there. So there's a table which rotates on a base which is bolted to the cross slide. There's just a simple block tool post with a tool and shims to get the height. Of course, the first project for the radius turning tool was to make a knob. Here it is in action. This is a 20mm radius, 43mm from the axis of the lathe. The material is 6061 aluminum. This is how to set the tool at a correct radius. So there's a datum post central on the axis of the tool, and just make a disc of the correct diameter to give you the right radius, and then bring the tool post up to the disc. Just touch it on a straight line from the axis along the tool, but just touch it, and then you can remove the disc and the datum post, and the tool will be set at exactly the radius of this disc. The idea being that you can just drill and tap a stud hole anywhere in the table as needed, and then you can move the tool to back and forth to adjust. I made the datum post with a threaded fitting and a large shoulder to try to keep it square, because of course if it's at all not square, then the position you put the tool in, if this is not vertical, then it will wobble, if you will, as the table turns, and the tool will not necessarily be in the right place. Probably I should have made it with a taper plug type of fit at the bottom. Maybe that's an improvement. But you can compensate. So if you just dial in put a dial indicator on the datum post and take the run out of it, and note the direction of the maximum and minimum run out, then you can correct for that on the lathe with the position of the tool, of the radius tool. But what I just showed was for an external radius. What about an internal radius? Well, the principle is the same, except that you cannot bring the tool up, because now the tool needs to be in this position with the cutting edge of the tool on this side of the disc, not this side. This side it will describe an external radius, this side it will describe an internal radius. So how to set the tool when this is in the way? The answer is to transfer the dimension. So I made just a simple transfer device, I don't know what you call this, and basically you just butt this up to the disc and tighten it, and then remove the disc and the datum post, and then just butt the tool up to the reference, and then the tool will describe an internal radius. The datum post is also used for setting the location of the center of the table. When you need a specific distance from the axis of the lathe or from the work, then you need to know where the center of the table is. So you use the datum post for that. Here it is just bumped up against a face on the work, which gives me a reference. Do the math with the known sizes of the work and the datum, and then set a stop so that the center is exactly in the right place relative to the work that you want. In this case, I'm making a worm gear, and I just want to put the throat in it. So I want the center of the table to be exactly in the center of the gear, where it's at right now. With this setup, you have to control one direction, if this is the X direction, and feed on the other direction, let's say the Y direction. It can be either way around. So here I've used the stop to set the X direction, and so that will be constrained. I will bring the carriage to here and lock it, but then I will feed the tool in and out to make the cuts using the cross slide. So the X-axis will be fixed and the Y-axis will move. I then need to control the Y dimension, but I'll do that by touching off the tool on the work, which then locates the tool, and then using a dial or the dials on the cross slide to do measure a depth of cut. But you need to set all that up beforehand because, for example, you can't bump the datum against the work, or reference the datum against the work when the tool post is installed. So this has to be done first, hence the stop. Then I can take the carriage away, do the tool post and the radius setting, and then bring it back to the stop and do the machining. Of course, you can always just use the tool to register against the work and locate the tool, but you have to make sure that the tool is at the point of closest approach, kind of like dialing in a curved surface. So the throat is supposed to be 22.23 millimeters. Let's just see. This is not a very good way to measure it, but I want to get an idea. And that's close enough for me. And of course you can use the radius disc that you set the tool with as a radius gauge. Here's the tool in another application. I need a radius, an external radius on this corner of this piece. It's 13 millimeters, about half an inch. And the diameter of this piece is 122 millimeters, about 5 inches. So now on a bigger lathe, I made a taller datum post. I got rid of the threaded, the datum post threading on, and I made it cylindrical, just a plug, and then just a couple of small screws to bolt it down. So that's better and a way of locating the datum post. I need the 13 millimeter, here's a 13 millimeter radius disc. So I need the center of the rotation to be 13 millimeters in from this outside diameter. So basically I just project that diameter with a parallel and set the position of the tool this way with the radius disc. In this case I'm struggling for clearance underneath the headstock. You can see I've cut the corner off the tool to get clearance. The tool is now mounted on a fixture plate which is mounted on the carriage. So I've lost the cross-slide freedom of movement. So I made slotted holes here and then just used those to adjust this dimension. This radius, the center needs to be about 48 millimeters off center of the lathe, nearly 2 inches. And then to set the other axis distance, because the center of the tool needs to be where this mark is, here. This surface here is conical, so it needs to be 13 millimeters that away from this surface to be tangent, so the radius is tangent to this conical section. And so I did the math and got an axial dimension from that. Then I'm projecting from this surface, from this point of the work, to find the location of the datum post, and then I will just move the required distance axially using the carriage, and dial gauge. I don't have a DRO on this lathe. Use dial gauge to move the carriage, the thickness, the dimension of the parallel to bring it to here, and then the required distance to bring it over to where it needs to be. So that's the setup for this particular radius. So there we go. That should be a 13 millimeter radius. Surface finish is not great because the material is mild steel, but there's play in the headstock bearings of this very worn out lathe, which I haven't fixed yet, so there was some chatter going on. But I think I tried to blend where the radius joins the cylindrical part with Scotch-Brite. It feels okay. So there's a female piece that will this will mate up to, and time will tell whether that's a good fit. But so far the radius tool has done what it needed, so pretty happy with that. So the table bears on a land on the base. There's a raised land here to give it some bearing surface and a lot of stability. And then the idea is that I don't want it to be able to lift or anything, so I put this, I don't know whether you can call that a dovetail or what. It's just a conical, a cylindrical piece of material with a conical section machined on it. You can see that the top there is the top of the cylinder, and the bottom of the cylinder, and then the conical section. And this is bolted to the bottom of the table, dowel pinned, and then extractor screws to be able to take it apart against the dowel pins. And the idea is there's a cylindrical bore in the base that bears on the two cylindrical portions of the this dovetail, I suppose, here and here. So you've got like a piston and a bore, and it shouldn't be able to move much, and it will keep it centered this way. But then to stop it lifting, I put in I can get one out. I put in pins that bear on, I guess, the dovetail and provide the holding down force while allowing the table to turn. And they're adjustable using these rather clunky, just push the pin in and then follow it with this and you can see that the pin extends into the dovetail, allows you to adjust the tension or the pressure of it, so you can tighten up or loosen off the amount of holding down or the amount of friction. And yeah, that's about it really. The pins, I for some reason had a good idea to put a threaded hole in the back of the pins, because once they're in there, they're pretty hard to get out without taking the whole thing to pieces and pushing them out from the inside. So pretty useful to be able to pull them out from the outside. And just a couple of other details. The material is all soft as butter hot rolled steel because it's cheap and I had it. So that means it'll wear up real quick. Better to make it out of something decent, or better still hardenable. It also, the fit is very close between this cylindrical piece and the bore here, and the soft steel catches when you're assembling and disassembling. It's really quite difficult. The other thing I would like to do is scrape the bearing surface so that it's nice and flat, and the corresponding surface on the table, so it's nice and smooth and flat and free. That presumes that I have learned to scrape, and I have not yet done that, so that's something for the future. In terms of rigidity and accuracy, I don't know what to shoot for, what to aspire to, but I've got an indicator here to measure, try and see if there's any lift, any play in the table. So I'm using both hands, and with pretty much almost as much as I can lift, I'm getting, I can get it to half a thou, but it's still, whoops, I just lost my indicator. And while there's not much play, it's still fairly easy to turn. This is the pinky test, so pinky finger to turn it means it's relatively free, but very little play, so that seems pretty good to me, and it performs okay. So one significant disadvantage of this design is that it's tall and it won't fit under the chuck. Here is the top of the cross slide, and the tool brings the height up so that it won't clear the chuck. So basically that's, well, something like that is as close as you can get to the chuck. That's nearly 2 inches away. So you'd have to have the work on a mandrel out here 2 inches out, which is a lot of stick out. You can support it with a center, but it's not entirely desirable. Or you can use a collet chuck, something, a smaller diameter chuck. So some form of collet chuck like this then gives you the clearance, and you can bring the tool right up to the work, or right to the chuck if you need to. This is just a homemade collet chuck, but anything would do, that smaller diameter. And one other advantage of this design is it can also be used as a sort of makeshift rotary table for milling. In this case, to put a radius on the end of a piece. So there it is, an adaptable radius turning tool that seems to perform okay. It's capable of doing internal and external radii up to about 75 millimeters or 3 inches, and to locate the center on axis or off axis wherever you need it to be accurately. and you can even use it on the milling machine for doing radii on the mill. So I hope you have found something interesting in the video, or even better, that it stimulates your own ideas. Bye for now.